This computer scientist has never built a bomb. He has never run a country into the ground. He has never killed anyone. He is actually a professor. You know, that type of person who is polite, soft-spoken, almost a bit shy. He's the kind of man you would expect to spend his life grading papers and drinking tea. And yet, the technology he brought to life now sits in weapon systems, mass surveillance tools, global financial markets, and systems used by hundreds of millions of people every single day. And that's not the worst part. Because the thing is, he now believes that the very thing he built has become uncontrollable. For decades, this scientist defended an idea even experts dismissed as naive. A theory about machines learning the way our human brains learn. The world moved on, but he didn't. Today, the once ridiculed idea is the foundation of modern artificial intelligence. And now, this same man is begging us to shut it down. This is the story of Geoffrey Hinton, the most dangerous computer scientist who ever lived. You may not believe it, but back in the 1980s, betting on neural networks was practically the same as career suicide. The field of artificial intelligence had already tried them once, and failed. Many researchers had promised thinking machines, but what they delivered were systems that couldn't even recognize simple patterns reliably. Funding agencies lost patience, and the media lost interest. It went into history as the artificial intelligence winter. And what do we know about winters? It kills things. Most scientists adapted. They moved into safer areas. Logic systems, expert rules, symbolic reasoning. Approaches that looked clean on paper. These were at least predictable and respectable. But Geoffrey Hinton, he chose the opposite path. He believed the brain had already solved intelligence. And no, not with perfect logic or clean rules, but with messy networks of neurons adjusting tiny connections through experience. The problem? Mathematically, it looked weak. Computationally, it was inefficient. Practically, it didn't scale. Everybody warned him that he was wasting his career, but Hinton wasn't trying to impress someone. He was trying to answer a single question. What if intelligence doesn't come from writing rules? What if it comes from learning patterns? For years, almost nobody listened, and for years, nothing worked well enough to prove him right. Until one mathematical trick, something we now know as backpropagation, quietly changed everything. But when it finally did, almost no one noticed. The thing was, one of the biggest problems in early neural networks was surprisingly simple. If a network made a mistake, how did you know which part of it was responsible? Inside the network are thousands, sometimes millions, of tiny connections. Each one contributes a little to the final decision. If the output is incorrect, which connection should change? And by how much? For years, this question made neural networks look impractical. But in 1986, everything changed. Hinton and two collaborators published a paper explaining how a method called backpropagation could solve that problem. The idea was elegant. You let the network make a prediction. You calculate how far off it was. Then you send that error backward through the layers, adjusting each connection slightly based on how much it contributed to the mistake. Not randomly, systematically. In this way, the network could improve itself. It didn't need new rules written by programmers, but it could learn from data. Today, that sounds obvious, but back then, nobody cared. The computers were too slow. The datasets were too small. The results were interesting, but not revolutionary. So once again, the world moved on. But here's the strange part. The method worked, and Hinton, he just knew it. For more than 20 years, neural networks were a side project. Interesting? Sure, but serious people didn't build their careers on them. It was simple. People tried. People failed. And it sure as hell wasn't the future. It was a dead end. But in 2012, something happened that most people outside computer science never even heard about. It was called the ImageNet competition. Researchers were given millions of labeled images and asked to build systems that could recognize what was in them. Dogs, cars, buildings, everyday objects, you name it. I know it sounds simple now, but you need to remember at that time, computers were still surprisingly bad at it. Most teams used carefully engineered systems, lots of handcrafted features, complex pipelines designed by experts. Hinton's team at the University of Toronto did something different. They built a deep neural network. And no, not some shallow one. I mean a large multi-layered network trained with backpropagation on powerful graphics processors. It was risky, since it required enormous computation, and many researchers still believed neural networks didn't scale well. But then the results came in. Their model didn't just win, it destroyed the competition. The error rate dropped by a margin so large that it forced the entire field to reconsider what was possible. Within months, every major tech company was paying attention. Within 2 years, deep learning was no longer controversial. It was dominant. After decades of defending a dead idea, Hinton was suddenly at the center of the most important shift in modern computing. And that's when the real scaling began. After 2012, things moved fast. Very, very fast. The deep neural networks that had just won ImageNet weren't limited to recognizing dogs and cars. The same architecture could be applied to speech, to translation, to recommendation systems, to anything that involved patterns. And suddenly, companies realized something. If you had enough data and enough computing power, these systems didn't just improve slightly, they improved predictably. Speech recognition, which had plateaued for years, started getting noticeably better. Online translation became more fluent. Search engines improved. Deep learning was no longer an experiment. It became infrastructure. Hinton joined Google after the breakthrough. His research group was acquired, and inside this big company, deep learning began spreading into product after product. But Google wasn't alone on this. Across Silicon Valley, every major player began reorganizing around the same idea. The logic-based systems of the past were quietly replaced with large neural networks trained on enormous datasets. And then something even bigger happened. Models stopped just recognizing patterns. They started generating them. Systems developed by organizations like OpenAI and Microsoft began producing text, code, images, even conversations that felt human. Underneath it all was the same core principle Hinton had defended for decades: layered neural networks trained through backpropagation at massive scale. What began as an academic theory had become a global layer of decision-making. And once something becomes infrastructure, it's very hard to turn off. Because what exactly happens if this intelligence starts evolving faster than the people who actually built it? For all those years, Hinton was known as the optimist, someone who really believed neural networks could achieve real intelligence when nobody else did. He argued they could outperform traditional systems. He pushed for bigger models, more data, more layers. And as we now know, he was right. But as these systems grew more capable, something shifted lately. Language models began writing essays, generating code, passing professional exams, creating images from nothing but a sentence. They didn't just recognize patterns anymore, they could simulate reasoning. For a while, it felt like this story had a clear ending. Everything worked. It was even profitable, embedded everywhere. From the outside, it looked like the ultimate scientific vindication, something you see in science fiction movies. But then, in 2023, something unexpected happened. After more than a decade working inside Google, Hinton made an unusual decision. He suddenly left, and not because the research failed, but because it succeeded. In interviews, he began saying things that sounded very different from the confident researcher of the 90s. Suddenly, he began to warn the world about misinformation at scale, about autonomous systems, about the possibility that highly advanced artificial intelligence systems could act in ways we don't fully understand. He admitted something even more shocking. He now was actually warning that they might be moving faster than we could ever understand. And this wasn't some outsider speaking. This was the scientist who made this whole thing possible. And when the architect of a system starts questioning its trajectory, they usually see something the rest of us don't. Calling Hinton the most dangerous computer scientist who ever lived isn't about drama. It's about leverage. We know that most scientists build tools. Good scientists build powerful tools. But there are just a handful of scientists who really change industries. And very, very rarely, some build a foundation. Hinton didn't create a single product. He didn't launch a social network. He didn't design a weapon. He helped revive a learning mechanism, a way for machines to adjust themselves based on data. That mechanism is now embedded in nearly every advanced system on the planet, and it's still improving every single day. That's what makes this different from past inventions. The scale is global, the speed is exponential, and the understanding is incomplete, to say at least. The most dangerous computer scientist who ever lived might not be the one who tried to harm the world. It might be the one who unlocked a system powerful enough to reshape it. So is Geoffrey Hinton really the most dangerous computer scientist who ever lived? Yes, but not because he wanted control, not because he chased power, but because he unlocked the scale. For decades, he believed intelligence could emerge from networks' learning patterns. He defended that belief when it was unpopular. He proved it when others had given up. And when the world finally gave in to his idea, it didn't just improve software. It reshaped infrastructure. Today, neural networks help decide what information we see, what loans get approved, how supply chains move, how surveillance systems operate, how weapons systems analyze data, how research is accelerated. That influence doesn't belong to one company or one country. It's global. And when something becomes global infrastructure, it stops being a tool you can casually unplug. Hinton is warning about these machines, about their speed, about their complexity, about systems that improve themselves in ways we don't fully understand yet. Systems that we may never understand. The most dangerous breakthroughs in history weren't dangerous because they were malicious. They were actually dangerous because they worked too well. And when an idea works at planetary scale, it changes the balance of power, whether we're ready for it or not.